complex. And if we are fast enough, I might want to go over a quick review on the d orbitals of transition metal centers. But today we'll be talking about 3 topics here. So first one is, what are we talking about when we're looking at a transition metal centers, or electron configuration of the transition metal centers and why they're special? This is more or less a review. The second part is bonding in transition metal complexes. So bonding in transition metal complexes is quite special comparing to the pure covalent bond or pure ionic bond. So I'll see a different type of bonding in transition metal complexes. And then we'll talk about molecular geometries of transition metal complexes. So first thing, transition metal complexes are, generally speaking, coordination complexes. And they are commonly observed in our body, in biological world, a lot. We talked about hemoglobin several times in stoichiometry problems already. But in hemoglobin is a protein that carries oxygen in our body throughout, your breath. So in hemoglobin, the reason it can carry oxygen around in our blood is because of these iron heme units in the hemoglobin protein. So I'm highlighted here. That's an iron-containing complex. So this is a typical type of transition metal complexes. And if we look at it, in here, we have 2 major parts. So apparently in the middle, we have an iron center or a transition metal center. And then surrounding that transition metal center, these are commonly called ligands that are binding to a transition metal center. So in real world, what happens is oxygen can bind onto the iron center, and then with that oxygen binding, the hemoglobin protein is carrying oxygen in your blood and give that oxygen to wherever your body needs it. So on this side, the typical method is when we're looking at transition metal complexes, you have a ligand, and groups that are making chemical bonds with that transition metal center are called ligands. So let's focus on the transition metal center first. As a quick review, in order to understand the transition metal center, you want to know the electron configuration of these transition metals. So this is a quick review. In previous studies, we mentioned that the 4s atomic orbitals are, generally speaking, filled before the 3d atomic orbitals. Likewise, 5s are filled before 4d and 6s before 5d, etc. So this goes back, again, as a review, why that is the case. So the reason behind 4s getting filled before 3d, even if 4s has a higher principal quantum number n, is coming from the shielding effect. So this is, again, a qualitative understanding on the origin of the shielding effect. When we're talking about shielding effects, again, what we have is the inner shell electrons will shield the center nuclear charge from the outer shell electrons. With d electrons, they have 2 angular nodes. So I'm just using the 3dxy here as an example. When you have more angular nodes, whenever you have angular nodes, means that there's 0 electron density at the angular node and very low electron density around that angular node. So the fact that 3d atomic orbitals have 2 angular nodes means they're going to shield the other atomic orbital less. In comparison, when we have s atomic orbitals, which are just spherical shape, they don't have any angular nodes. So the s atomic orbitals will shield the nuclear charge more comparing to other atomic orbitals. So the result here is, if we're comparing the energy of 4s and 3d. This is, again, the same equation we're using. So for 4s and 3d, we know that n equals to 4 for 4s, n equals to 3 for 3d. So if we're just looking at the quantum number n, we know that the 4s were expected to be higher in energy comparing to 3d. But because of the shielding effect, we have this the effective term. So the 3d is more shielded comparing to 4s. Nevertheless, so these are just the rationalization behind this trend. The take-home message is that the 4s is always filled before 3d when we're putting electrons in there. Or, in general, most of the transition metals will have the electron configuration with some noble gas, and then you have the n-1 with the x electron, and then the s atomic orbitals are more likely to be filled first. You can also write it as like ns in front of n-1 xd. It doesn't really matter in this class. And occasionally, you would also have situations where your s atomic orbital is singly occupied. So these exceptions takes place when you have like chromium and copper. So you see chromium as an example and just think about why in chromium you have the s orbital singly occupied. So remember what we were talking about. This is a little bit of the extra I'm not going to test you on, but it's nice if you understand why that's the case. So when we look at the chromium case, what we have is 4s, slightly lower in energy, comparing to your 3d. So for chromium, how many valence electrons do we have? So we have a total of 6 electrons in the chromium valency. So when we put it in, we have 1, 2, 3, 4, 5, 6. The reason the 4s is singly occupied for chromium is we're avoiding that electron pairing energy. Nevertheless, that's a little bit of the extra. Just like take one more step and think about what's the origin behind these trends instead of just trying to remember it. And then the next topic is again some review when we're talking about the transition metal cations. So this is again something special about transition metals. When we're putting electrons in, we put it into the s atomic orbital first. But when we're taking electrons out to form transition metal cations, electrons in the s orbitals are removed before electrons in the d orbitals. So we'll use iron as an example. If we have neutral iron atom, the electron configuration is argon, and then 4s2, 3d6. Did I do that correct? Yeah. But when we're taking electrons from the neutral iron, we're taking it from the 4s first. So iron 2 will be argon 3d6. Iron 3 will be argon 3d5. So when we're writing the oxidation or the transition metal cations, you have two different ways to write that. You can either write it as like iron 2+, which is typical, or for transition metals, you can also write it with the capital Roman letter. So this capital Roman letter 2 means it's iron 2+ cation. All right. So how are we doing about this review here? We covered this when we talk about electron configuration, but this is just a quick refreshment on what we discussed before. All right. And then came to the point of understanding why transition metals complexes are special. Transition metal complexes are special primarily because they have so many different oxidation states. So if we're looking at the main group elements, say if we have a oxygen or a fluorine, you can pretty much guess what the oxidation state for that element is. But for transition metals, these oxidation states or the formal charge have so many different choices. So you don't have to remember any of this, but this is just a table to show you what are the available oxidation state or possible oxidation state for different transition metal complexes. There are still some trend, but the take-home message is almost all transition metal complexes or almost all transition metal centers have multiple allowed oxidation states. So when we're talking about transition metal center, when we're describing the transition metal center, so far we discussed two different ways to describe it. You can have the electron configuration, you can have the oxidation state, and then we also use the electron count to describe the transition metal center in a complex. So this is actually related to oxidation state and electron configuration. It's just another notation people use to describe a transition metal center. So what it means, let's just use, say, zinc 2+ or zinc 2 as an example. And we look at it, zinc is numbered 30. And we write the electron configuration here. That's argon, 3d10. Right, it used to have 4s2, but we're removing those 2 electrons because it's a zinc 2. So if we're looking at the d electron count, what we're doing is we're counting the electrons in the d atomic orbitals. So the d electron count in zinc 2 will be 10. All right. Some more example here. We can have rhodium 3. So rhodium, let's just find that, that's number 45. That's chromium, 4d. Well, it's 4d7, 5s2, but it's 3, so it goes down to 4d6. And the d electron count is 6. One more example, we can have iron. So now we're using iron 5. And that's chromium, well, that's argon, sorry. Three D3. So d electron count is 3. All right. So I'm going to quickly pause here. This is just a very shallow review on what are the things we use to describe a transition metal center. Briefly, you're expected to know how to write electron configuration of a transition metal center, to know how to derive oxidation state, and know these transition metals always have multiple oxidation states that are available. And then know how to derive the electron count by writing out electron configuration of transition metal cations. Any questions before we move on? Okay, sounds good. And now let's move on to our second topic, which is chemical bonds in transition metal complexes. So transition metal complexes, again, like what we said before, usually we have a transition metal center, and then we have ligands or other chemicals that's binding to your transition metal center. So these transition metal centers, typically cationic with a positive oxidation number, are often stabilized when they make a chemical bond between a ligand. So I'm just showing here 2 examples, and we'll come back to talk about each of these 2 examples as a whole. On the left, we can have chromium that's binding to 6 different chloride ligands, making a chromium chloride 6. Or on the right-hand side, you have cobalt binding to ammonia. So These two examples are actually a demonstration of different kinds of chemical bond between a transition metal center and a ligand. What are the typical type of chemical bonds we're talking about? So we're just focusing on the classical bonding theory for the transition metals for now. It's getting too complicated when you draw the MO correlation diagrams. Like what we said before, in classical bonding theory of the main group element, we discussed two different types of chemical bond. We can have ionic bond. We can also have covalent bond. So ionic bond is also available in transition metal complexes, forming a crystalline-like of complex. So I'm just showing here a zirconium dioxide or ZrO2. So in the zirconium dioxide, these crystals has chemical bonds or ionic chemical bonds between zirconium, which is a transition metal, and oxide. So the zirconium oxide gives you a very regulated crystal structure, and that's why these stones are pretty. So that's the ionic bond. But we won't talk too much about the crystallization, the crystalline nature of these ionic complexes. More typically, in transition metal complexes, especially in solution phase, you have polar covalent bonds. Like the main group elements, when transition metal centers form a covalent bond with another atom, what we have is each bonded atom contribute one electron to make that chemical bond. It's pretty similar to what we're talking about when we have when we're drawing the Lewis-Dot diagram for, like, say, CH4. So what you have is carbon and hydrogen each donate one electron to make a chemical bond. In the polar covalent bond cases, with the transition metal center, that's the same idea. You have the transition metal and the ligand each donate one electron to form a covalent chemical bond. So these are the examples we were talking about. We're just making the comparison between a polar covalent bond in a transition metal complex and a polar covalent bond in a regular organic compound. So in each of these cases, imagine that's a Lewis-Dot diagram. What we have on the right-hand side, that's a regular covalent complexes, right? The carbon is given one electron to make a chemical bond, and chlorine is given one electron to make that chemical bond. So if we're writing the oxidation state for the carbon and chloride on the right structure here, what we have is we know chloride that's a halogen, so it's likely to be -1. And carbon, that's +4. Again, this is oxidation state. We're not talking about formal charge or anything. This is just oxidation state. It's different from formal charge, so don't mix them up. So we can do the same for our transition metal complexes on the left-hand side, right? So for each of the chlorides, we're expected to have a -1 oxidation number. And then the oxidation number on the center chromium is likely to be +6. Again, we're talking about oxidation state. Or in transition metal complexes, these covalent bonds are named anionic bonds. Or anionic ligand. We also call them X-type ligands. The other way to depict the covalent bond in transition metal complexes is, say, if we have a metal binded to a transition to a anionic ligand or X-type ligand, And when we break that chemical bond, what we're having is N plus and X minus. So this is a good way of thinking about whether it is an anionic bond. So the take-home message is if we break this chemical bond and both electrons goes with the ligand, and you look at that ligand, does that ligand have a formal negative charge? If it does, then it is an anionic bond, an anionic ligand or an X-type ligand. Right, so what we have here, for example, if we break this chromium chloride bond, what we end up with is, say, chromium, just one of them, chlorine plus Cl with 8 electrons, and that has a negative formal charge. So that's just a justification in how to identify whether or not a ligand is an anionic ligand. We have some typical examples of anionic ligand. Or X-type ligand. So these are like fluoride, bromide, chloride, or your halogens, cyanide, and OH minus. So that's one type of the transition metal bonding with a X-type ligand or an anionic ligand. It's a covalent bond. And then we're moving on to talk about another special type of chemical bond in transition metal complexes that's called dative bonds. So the dative bond is a special type of chemical bond that's almost only available in transition metal complexes. So in dative bond or a donor-acceptor bond, what we have is a lone pair of the electron on the ligand donates both of its electrons to an empty orbital on the transition metal. So both electrons in that dative bond comes from the ligand. All right, so that's the major difference here. In the dative bond, both electrons in that chemical bond, in that dative bond, comes from the ligand. So this is the cobalt hexammonia we talked about. And what does that chemical bond actually look like? So a oversimplified version of that is cobalt. And then your NH3, if you draw the Lewis dot diagram, it has a lone pair and 3 NH bonds. So what we're proposing here in making this dative bond, this lone pair of the NH3, both electrons in that lone pair donate its electron density into empty orbital of your d atomic orbitals of cobalt. So this is, again, a dative bond. So the interesting thing about dative bond is it doesn't change the oxidation state of your center atom here. So if we look at it, these NH3, they're just neutral species. And the fact they're just donating both its electron into the transition metal center, it doesn't change the oxidation state. So if we write out electron configuration, these are just all 0. And then your metal center will have a +3 oxidation state. That comes from here. Or the other way to put it is when we're talking about a dative bond between a ligand and a transition metal, what we have is neutral ligand or we can also call them L-type ligands. again, the way we picture or identify whether or not that ligand is an L-type ligand is imagine you have a metal ligand bond. And again, you cleave that chemical bond and all electrons go to the ligand. You end up with two neutral species. All right, so what we have here is again depicting this specific chemical bond. If we cleave this chemical bond and both electrons go to the NH3, your NH3 with the lone pair is again a neutral species. So that is why in dative bond, in making dative bond, we're calling these ligand neutral ligand or L-type ligand. So typical L-type ligand will have lone pairs to bind onto the transition metal center. Again, these are neutral ligands. So you can imagine molecules with lone pair like water, ammonia, pH3, or even an alkene. So this one is a little bit special. It doesn't have lone pair, but you have p orbitals that can donate electron density into a transition metal center. So if we write that out, what we have here, you can have a PMO that donates electron density. All right. We'll do one quick example together, and let's see if we have questions. So this question is quite short. We're just talking about can you identify the oxidation state of the cobalt center in this complicated complex. So in this complicated complex, the first thing we want to do is is what is the actual structure of my transition metal center. So in this case, my Br2 that's outside that bracket, so that is our counter ion. That's not part of our transition metal complexes. So when we say it's a counter ion, that does not, what it means is this bromium does not bind the cobalt directly. So removing that counter ion, our actual cobalt complex has cobalt, NH3 H2O, Cl, and 2+. And then we can go into that transition metal complex and identify different types of the ligand. So in here, chloride, that's our X-type ligand. Or anionic. So this will have a -1 oxidation number. And then the ammonia and water, these are our L-type ligand. Or neutral ligand. So they do not change the oxidation number of your center atom, which is cobalt in this case. So as a whole, we can identify that my cobalt center will have a +3 oxidation number, or you can write it as cobalt 3. Apparently, you can easily imagine this problem to be associated with either electron configuration or d-electron count, right? Can you write the electron configuration of the cobalt center in this transition metal complexes? Or can you give me the d-electron count of the transition metal center here? All right, I'll pause here for any questions you might have. Yeah.
Why don't we include bromine when we're doing that?
Yes and no. So we did include bromine. We have two counter ions. When we say it is a counter ion, what we mean is that counter ion does not directly bind onto the transition metal center. So imagine you're in a solution, then this part will be binded together as a complex, but the bromine anion will be surrounding it, not directly bind onto the transition metal center.
Okay. It doesn't bind CO directly.
It doesn't bind CO directly.
Oh.
Yes.
How can you tell that ammonia and water are an L-type ligand?
So this goes back to when we were talking about the L-type ligand. Again, we use ammonia as an example. We can write the same as for water, right? Imagine in that example we have cobalt, and then we have oxygen, water, that has lone pair. So in this interaction, in the dative bond of oxygen lone pair to cobalt, both of the electron of that chemical bond comes from water, where water is a neutral molecule. So that is a L-type ligand, it's a typical neutral ligand. Yes?
How did you know that charge of the complex was 2 exactly?
That comes from the two counter ion here. We have two counter ion, both of them are halogens, so that goes to 2 minus. All right. So that's the 3 different type of chemical bonds in transition metal complexes. Ionic complexes we didn't cover too much about it. The take-home message is if you have an ionic complex with transition metals, it's likely to be a good crystal. And if we're talking about solution phase, the covalent bond and the dative bond are more important. The covalent bond is like what we have, the covalent bond in the main group molecules. It's a X-type ligand, it's anionic, and if you break that covalent bond, what you get is a metal cation and the ligand anion. And then we also have the dative bond, which is special for transition metal center. For dative bond, what we have is a donor-acceptor bonds. Means your ligand is donating both of its electron pair. Normally it comes from a lone pair or p electrons, or pi electrons, I'm sorry. So we gave several examples, like NH3, water, pH3. These are donation from the ligand lone pair, or alkenes, where you have a pi electron that can donate into a transition metal center. To form these covalent bonds, they're typically neutral. It doesn't change the oxidation state of your transition metal center. So moving on to our next topic, which is multidentate ligand. So far we were just talking about the ligand is binding onto the transition metal center, right? One ligand binding onto the transition metal center with one binding set. However, in real life, we could have multidentate ligand. What does multidentate ligand mean? Is that you can have one transition metal center, but the ligand associated with it can make multiple bonds to that transition metal center. So what we discussed before, like ammonia or chloride, those are called monodentate ligands. A monodentate ligand only make one chemical bond with the transition metal center. But when we're having multidentate ligand, what it means is that ligand can form multiple bonds with a transition metal center. So let's look at a bidentate ligand, for example. Bidentate, judging by its name, it just says this ligand forms 2 bonds to a transition metal center. So the example of a bidentate ligand we're talking about is an ethane enamine. So in this complex, each En will have 2 chemical bonds with the transition metal center via the lone pair of its terminal amine group. So when we're drawing these dative bonds, what we have is these are the lone pair that's donating electron density into the center palladium. Right, so surrounding the center palladium, how many ligands do we have? Right, so in a total, we have 4 L-type ligand binding onto the transition metal center. That 4 L-type ligand comes from 2 bidentate ligands. All right, so if we're counting the coordination site, in total, we have 4 L-type coordination site onto your transition metal center. And that 4 coordination site comes from 2 bidentate ligands. Each bidentate ligand affords 2 coordination sites. All right. So let's look at a more comprehensive example, which is going back to our hemoglobin again. So let's read it together. It looks really long, but the actual idea is quite straightforward. What we have is in the introduction, we know that a typical hemoglobin ligand is a tetradentate ligand. By say tetradentate, we're saying there exists 4 chemical bonds between that ligand to the center atom. I'll show you the molecular structure of hemoglobin again. But here are the things I want you to think about when we're looking at that structure. First thing, for all the nitrogen, add the lone pairs and partial charges so they have octets of electron. So that's the first step. And then identify each nitrogen to be whether X-type or L-type ligand. Again, X-type is anionic, L-type is neutral. And then at the very end, solve for the d electron count of the iron center in this complex. So we'll just do it together here. In this nitrogen here, right now this nitrogen is making 2 single bonds with its neighboring atoms. So in order to make this nitrogen have 4 octets of electrons, we need to add 2 lone pairs. And if we're counting the electrons and the formal charge on that nitrogen, we have a negative formal charge. All right, so what we're doing is first add the lone pairs so the nitrogen have octets of electrons. And then we add the formal charge accordingly. For other nitrogens, we can do the same, but on the left-hand side, this one is making 1 single bond and 1 double bond, so we only need 1 lone pair, and this nitrogen is neutral. On the bottom, this nitrogen has 2 single bonds, so we need 2 lone pair, and this one has a -1 formal charge. And on the right-hand side, we have a neutral nitrogen again. So naturally, we have 2 different types of ligand. So these 2, where I highlighted in green, are anionic, or what type of chemical bond we're making here. Again, anionic, X-type ligand, it's covalent bond with the center iron. So when we draw it, we just draw it as a covalent bond. Alternatively, you have 2 more nitrogen that are neutral. So these neutral nitrogen will form dative bonds with iron. We use a little arrow to represent dative bonds. So these are L-type ligand or neutral ligand, and they form dative bonds. All right. And then if we're looking at that iron center there, apparently it has a iron 2 because we have 2 anionic ligand binding onto the iron center. So the iron 2 will have the d electron count of 6. So the procedure is first write the lone pair and formal charge so your ligand have octets of electron. And then depending on if they're anionic or neutral, you have X-type or L-type ligand forming covalent or dative bonds. At the end, you can also derive information about oxidation state and d electron count of your center atom. All right. We're doing good on this one? Okay. Last topic, molecular geometry of transition metal complexes. So again, this involves some three-dimensional sketching. We know that our molecules are actually three-dimensional, right? It's just not on paper. We're living in a three-dimensional world. So when you're drawing the molecular geometry, this is similar to the VSEPR example we did before. You have different geometry of these transition metal complexes. And depending on the relative position of your ligand, you can have different conformations. So we're using the octahedral geometry as an example, which is a 6-coordinated complex. So in the 6-coordinated complex, we have 3 ammonia, 3 chloride. Just quiz here. What's the oxidation state of cobalt here? Any guess? So raise your hand if you think it's +1, +2, +3. Yes, we all get it right? So just a quick refresh, like how to quickly determine the oxidation state. So there are 2 different ways you can orient these L-type ligand and X-type ligand, or different kind of ligand. So in this case, if my chloride is trans to NH3, this conformation, we call it FAC. And on the right-hand side, if you have a chloride that's trans to another chloride, we call it MER. So the relationship between these 2 structures, they have the same molecular formula, but different 3-dimensional structures. So the relationship here are called 2 different conformations. So by say conformation, what we mean is that they have same molecular formula, but different molecular geometry. Or the 3D orientation of the ligand. So these 2 are just different conformations. So that's the notation for the octahedral conformations. We could also have square planar complexes. So square planar complexes, they're square planar, so it's 4-coordinated. We typically observe square planar geometry in late transition metals. This part you don't need to remember. It's just I'll always tell you what the geometry is. But what you want to know is, looking at these 2 geometries, can you label them with the correct notation? And can you tell what's the difference between these 2 geometry? So let's use the palladium with Cl2 chloride and 2 iodide. Right, so in this case, again, a quick survey here. This is a +4 because both chloride and iodide are X-type ligands. So in this drawing, what we can say is you have chloride cis to iodine to 1 iodine and 1 chloride. So that's the relationship we're talking about. Cis just means chloride is in close proximity to another chloride and in close proximity to another aldyne. Or alternatively, on the right-hand side, you have a different structure where the chloride is trans to another chloride. And this is cis. So to two iodines. So just some notations that will come useful. Cis just means this ligand is close to another two ligand. Trans just means this ligand is 180 degrees to another ligand like that. All right. Transition metal complexes can also be tetrahedral geometry. So again, early transition metals tend to have tetrahedral geometry like chromium, magnesium, and iron. So when we're drawing the tetrahedral geometry, as a quick example, let's use iron. Likewise, we have 2 chloride, 2 bromide. Imagine that has a -1. So how do we draw it? So if it's a tetrahedral, we put the center iron in the middle, and then you have chloride, and bromide coming wedged out and dashed in, and my entire molecule might have a -1 charge. So when sketching these tetrahedral geometry, this one is actually symmetric. It doesn't matter where I put my chloride and bromide. There's only one conformation here. I think that's all the time I have. There is a sample question that's left in your annotated notes, so work on it if you like. All right.